This is the fourth and final section on the chapter on work, energy and power, and here we look at power, and we've got this equation here. Power is force times velocity. So quite often in these questions you'll see that the things are traveling at a constant speed. Yeah, so that's where we'll get V from. And you may find it more helpful to rearrange this if I use P for power and then actually say, right, your force is equal to the power over the velocity. Yeah, now the advantage of using that is that if you've got a question where, I don't know, you've got an object that's maybe going up the slope, let's say it's going at a constant speed that way, then the force that's making it go that way, well, that's going to be your P over V. Yeah, we normally talk about, let's imagine that this is a car here and it's got an engine. Yeah, and we might talk about the power developed by the engine. Power developed by the engine. And that power developed by the engine will be given in watts or kilowatts. And that's what's going to go here. So if it's kilowatts, it just means you times it by 1,000. If it's traveling at a constant speed, well, you divide it by whatever that constant speed is. And basically the power developed by the engine divided by the constant speed that it's moving will give you the force here, which you can then use in terms of just using things like F equals ma, just like looking at your forces being balanced or unbalanced. Yeah, so if this is traveling at a constant speed, then actually in this particular example F would equal mu r, or if there's we're looking at this force here, let's put theta in. Put theta in there. Let's have m for the mass of it. Then actually then if it's traveling at constant speed, that means the forces are balanced, and the force going up would be F. The force going down would be, let's put here mg cos theta, and this would be mg sine theta. So force going up is F. That would equal the forces going down, which is mg sine theta, and the mu r, for example, or the frictional force, and then F, because F is just power over velocity, so we've got something like this. So basically the whole point of that was to say, really use that. That's fits in with what we've been doing with forces. A truck is being pulled up a slope of constant speed of 8 meters per second by a force of magnitude 2,000 newtons. Right, okay. Up a slope. Right, there's my truck. Constant speed of 8 meters per second. Okay. The force is 2,000 newtons. Calculating kilowatts, the power developed. Okay, so power equals FV. So that's just going to be 2,000 times 8. So that's 16,000 watts, which is 16 kilowatts. They want the answer in kilowatts, so 16 kilowatts for that, and you can just write it as 16 kW like that. That's absolutely fine to leave that as your answer. On this one we have a van which is travelling on a horizontal road like this. It's got a mass of 1,250 kg. We've got the power developed by the engine, so let's say it's going this way, of 24 kilowatts. So 24 kilowatts, and there's a resistance to motion of 600 newtons like this. So part A, it says calculate the acceleration of the van when it is travelling at 6 meters per second. So the first thing is that we can work out basically the pulling force of the engine by doing this. So when the van is travelling at 6 meters per second, the pulling force is going to be this 24 kilowatts divided by the velocity. So 24,000 divided by 6 is going to be 4,000. So the pulling force of the van is 4,000 newtons. So now we can use F equals ma. So the resultant force is going to be the 4,000 pulling force minus the 600 resistance equals ma. 1250A. So A will equal 3,400, that's 4,000, take away the 600, divided by 1250, and we should get an acceleration of, let's have a look, (68/25), which is 2.72. So A equals 2.72 meters per second squared. Right, so that's the acceleration when we have a velocity of 6 meters per second. So what we did was we worked out basically the pulling force of the van at that velocity, and then once we've got that, we just use F equals ma, resultant force equals ma. Now obviously if the van was travelling at a different velocity, then we'll have a different pulling force and a different acceleration. Yeah. Now part B, the maximum speed, right. What goes on at maximum speed? At max speed, maximum speed, the acceleration is 0. A equals 0. Now what does that mean? That means that the pulling force and the pulling force will equal the resistive forces. They will be balanced if it's travelling at the maximum speed. So the resultant force basically will be 0. So we've got the pulling force of the van will equal the resistive force, which is 600. So we can say, well, P over V equals 600. Yeah. So P, the power of the engine, is still 24,000 over the V, which we don't know, that's going to be the maximum speed, equals 600. So V is going to be 24,000 over 600. And that gives us 40. So maximum velocity of this fan is 40 meters per second. So don't forget, when at the maximum speed the acceleration is 0, that means resultant force is 0. The forces, the pulling and the resistive forces will be balanced. Right, so we'll start with a diagram. So this time it's a car inclined at 7 degrees going at a constant speed of 15 meters per second up the slope. It has a mass of 1,100 kilograms, and in the first part of the question it is the engine is developing a power of 24 kilowatts, and we need to work out the resistive forces. So I'm going to call the resistive force F. Don't want to use R in case we confuse that with a normal reaction. Right, so let's think about what this engine needs to do. So it needs to overcome the frictional force, and it also needs to overcome the weight of the car going up the slope, and that is going to be this component. Now, since this is 7 degrees here, this other force, which is also, as you see, running parallel to the plane that it needs to overcome, is going to be 1100 G sine 7. Yeah. Now, since it's traveling at a constant speed, that means the resultant force is 0. So the resultant force of the 24 kilowatts changed to a force, and F and this component here, they're going to be balanced. So what does that mean? That means that the pulling force, which is P over V, the power over the velocity, which is 15, been given that there, equals the gravitational force, which is the 1100 G sine 7, and the frictional force of F. So now it's just a matter of rearranging it, so we can say F equals P over V minus 1100 G sine 7, and P over V is 24,000 over 15 minus 1100 G sine 7. So this can just be put straight in on the calculator to work out what F is. So 24,000 over 15 minus 1100 G, 9.8, times sine 7 degrees, and I get 286.248. So let's have three significant figures. So we'll say F is 286 newtons for the frictional force. Okay, part B. Now, just before part B, there's some extra information, and it says that the rate of working of the engine is now increased to 28 kilowatts. So let me rub out that 24 and change it to 28. I'm just going to use the same diagram again. So 28 kilowatts. Assuming the resistances are unchanged, calculate the initial acceleration. Now this time, because it's accelerating, that means that the forces are not balanced, that the 28 kilowatts as a force P over V minus this component and the frictional force 286 is going to equal MA. So we now have a resultant force. So that's going to be, so we'll write it as P over V minus minus the 1100G sine 7 and F is going to equal MA. Yeah, so let's put all the numbers in so we can get the answer. So P is 28,000, V 15, this is the instant where the power has changed, it was travelling at 15, minus, well that's still the same, that component of the force, minus F, well that's the 286, but I want to try and use the exact answer if I can, and if I say right, divide that all by the mass 1100, that will give me A, which will enable me to do it all in one go. Now I've just got the previous answer, so I'm actually going to just type it all in as one. So 28,000 over 15 minus 1100 times 9.8 times sine 7 minus, I'm just going to press answer, 286 all over 1100, that's 8 over 33. So I could leave it as exact as 8 over 33 meters per second squared, or as a decimal it's recurring 0.242424, so 0.242 meters per second squared. So either one of those as the final answer would be fine. So I'll just leave that there. Okay, this time we got a car of mass 2,600 kilograms traveling in a straight line. Now this time it doesn't seem to be on a slope, not in part A anyway, so maybe I'll need two diagrams. So it's traveling in a straight line like this. Its mass is 2,600 kg. At the instant when the car is traveling at V meters per second, so that's its velocity. Total resistance is a variable frictional force, which is actually 800 plus 5v squared. So as the velocity increases, the frictional forces increase. The car has a cruise control feature which adjusts the power generated by the engine to maintain a constant speed of 18. So in part A it's travelling at 18. Okay, find the power generated by the engine when the car is travelling on a horizontal road. Right, so we want to find the power. So that pulling force of the car is going to equal P over V. So because we want to find the power, we could say the power equals FV. Now, if it's travelling at a constant speed, that means there's no resultant force. The pulling force is equal to the resistive forces when it's travelling at 18 meters per second. So the pulling force is going to be P over V. That's going to equal the resistive force, which is going to be 800 plus 5v squared. So now we can put our numbers in. V is 18, so we'll have P over 18 equals 800 plus 5 times 18 squared. So P is just going to be all of that times by 18. So let's work that out and see what we get for that. So 18 bracket 800 plus 5 times 18 squared, and we get this 2, 3, sorry, not 2, 3, I put 800 times, I put times on my calculator there by mistake. Right, so it's 4, 3, 5, 60, 4, 3, 5, 60 watts, If we could give it in kilowatts, couldn't we? So 43.56 kilowatts. I think that's right. Okay, so that's part A done. Now what happens in part B is that the car is now travelling on an incline, so we're going to need a new diagram. And inclined at 4 degrees, so that introduces a new gravitational force that needs to be overcome. It's still going to be 18, which means the frictional force here will be 800 plus 5 times 18 squared. So I'm running out of space now. Actually, let me redraw that so that it's a little bit clearer. So actually, let me just write it as 800 plus 5 times 18 squared. That's a bit better. So that's the frictional force there. We want to calculate the power, which is going to be P over V. Well, actually, it's going to be, well, let's just put this as P over V here for the minute. And actually, we can put P over 18, can't we? But what we now need to include is the weight of the car, and we're interested in this component here, and because that's 4 degrees, this will be 2600 G sine 4. So we're now ready to write our equation. It's traveling at a constant speed, so the P over V is going to be balanced with this component here and this frictional force here. So now let's write down that P over 18 equals the 2600 G sine 4 plus the frictional force of 800 plus 5 times 18 squared. So P, we can just work out all of that, times it by 18, so 18 times by all of this. So let's put this on the calculator and see what we get. So 18 bracket 2600 times by 9.8 times sine 4 plus 800 plus 5 times 18 squared, and that gives me 755310912. Okay, so I suppose we could leave it like that. We could go for 3 significant figures, but I would tend to probably leave that as a full answer. Probably knock the decimals off the end and say that's 75.553 kilowatts on that one. Yeah, you can leave it as watts or kilowatts, it doesn't really matter. So let's stick watts down here. Right, you should now be able to do exercise 2D on pages 31 to 33 of the textbook.